Hi everyone, and first of all, I'd like to thank to the organizers, Nicolas, Etienne, Gilles, and myself, right? That's how we started on Monday. It has been wonderful even more than 4 years that we've been organizing this, so finally we're here, so that's great. And then I have to, I would like to say a few words about Denis. As Sylvie said, I did my PhD with Denis in Sofia. And it was a great 3 years at Tosca team. I can talk about it a lot, but I'll try to give just a few elements. So for me, my experience with the PhD with Denis was like a perfect combination of autonomy and interaction. So the first day I came to Sofia, Denis came to my office, and he was living for 3 weeks in another part of the world, and he told me, this is the book of Karatas and Shreve, and this is the paper of Bossitale on the Burger's equation, this is the paper of, this is the Sneedman theory of propagation. You should read the course of Sneedman, and then there's the paper of Fournier-Jourdan that you've listened about. So here are all these elements, and now I am going away. I'll come in 1 month, and we can talk about it. Okay, great. Then another example of pure autonomy was just at the end of my thesis. I was finishing the chapters, and I really eagerly wanted Denis to read the chapter, but he claimed that he already seen that, and at some point he was like, c'est pas ma thèse, c'est la tienne. So it was great as well. And I tend to apply that for the future, because yes, it was my thesis and not his. So, and I was happy actually at the end that he let me do the things by myself. But on the other hand, every time I did a queue in the canteen for lunch, and Denis was in the queue, he would ask me, how is it going? How are my computations going? Where am I? And if I am blocked somewhere, he would be so kind to say, okay, let's see after lunch, where's your problem? And we would speak in his office, even though I haven't booked my slot 2 weeks in advance, like usually it's with Parisians that have to speak with their advisors. So that was amazing. And then I learned a lot from Denis, but I also learned a lot about France from Denis. And Denis was actually the first person who spoke math in French to me. So if you have problem in understanding when I speak in French about math, you should thank to him. So yeah, it was really great, and after that what remained is a great relationship as well, and I appreciate Denis a lot, and also I appreciated the environment of Tosca team and all the people that were there at the moment, and actually being far away from my family and in another country at the time, Tosca was kind of a reference and kind of like a familiar place where if there was an issue, I could turn to them and it would have been solved, and that's something I really appreciated. Okay, so I'll stop with that, and I remember Quentin said this morning he never saw Denis wearing a casquette. I'm not sure about casquette, but I've seen Denis wear sneakers. Okay, and that was in New York in Central Park when we were doing maths in Central Park. But maybe you even had the casquette. So I don't remember. And also, many people said that they had difficulties finding photos of Denis. So I'm not in that category. I can find a photo of Denis because it was just recently that I was in the Tosca team, and then I have a mobile phone, right? You didn't have it in the 80s, so that's why you don't find the photos. So I don't just have a photo of Denis, I have a photo with Denis. So voila, there it is. So this was just after I got my report of my thesis. So, okay, so then maybe I stop here. and I can now speak about math. So I want to talk about the propagation of chaos for particles in LQ-LP interaction. So the first thing, just a small reminder and something that we all know, but just to introduce the things, and we've seen in the previous talk. So if you start with a particle system, where's the thing? That for me, they always have a constant diffusion coefficient. And then the particles are interacting through a function B, right? Where 2 by 2, so we have the interactions, and the drift may depend on time as well. So, and if you have reasonable assumptions on B, like bounded Lipschitz in space and bounded in time, whatever, you can prove that the empirical measure converges towards the law of this nonlinear stochastic process. Okay? And so at the limit, when you send n to infinity, you find this nonlinearity here, so X interacting with its law, right? And of course, if you take the marginals of the empirical measure, they're going to converge to a PDE, right? Very long history in the literature about it, which I don't want to review. But you've seen that in the previous talk, that usually like physical examples are going to lead you to singular interactions. So if you work with a PDE, if you want to give a probabilistic approach to a PDE, which models some physical phenomena, there's like usually something you're modeling is a bit singular, and the equations are not that easy to discretize, and the coefficients are irregular. And so the singular nature of coefficients, like the first questions you have to ask yourselves, and it's what you've seen in the previous talk as well, is whether your system is well defined, whether the limit is well defined, and can you connect the two? And then you can go and ask yourself many sophisticated questions about your particles and about the physical example, like do they collide, how much they collide, etc. But if you have singular coefficients, you first have to prove that things are well defined. And it usually comes from some physical examples. So here today, there's not going to be really a physical example that's going to motivate us, but there is going to be a theoretical condition from the literature that we are going to be motivated by, and that's the condition of Krylov and Rockner. So Krylov and Rockner, they proved 2005 strong existence for linear processes of just one particle, let's say, in dimension D, which have a drift that has some integrability properties. So integrability properties in the following sense: some LP integrability in space, and then what you get, it's you take the LQ norm in time, and that's finite, okay? And there is a condition that relates the exponents of regularity here and the dimension in which you work with, and that's this relationship here. And they established so strong well-posedness for these equations. And it's kind of a general condition, and it's not necessarily something that's Lipschitz continuous, but still you have strong well-posedness, okay? So it's not like usually the coefficients, when you look at the books of stochastic calculus, you have something continuous and Lipschitz and bounded or whatever. But here you have something that's not necessarily Lipschitz, but this at least. Or not necessarily, it can be singular, it can be unbounded, etc. But as long as it's integrable in this way, you're fine. And then recently, for nonlinear equations, so in the framework of the Mekin-Vlasov process, Rockner and Zhang, they proved a similar, so they extended the results to nonlinear equations, so the Mekin-Vlasov processes. So like in my first slide, the Mekin-Vlasov limit, so there's this B, and if B is dominated by a function that's in LQ-LP with the same conditions, and if you put something on the initial condition, you have strong well-posedness also for this Mekin-Vlasov equation, okay? So our goal today, no surprise there, is going to be to look at the particle system related to this equation under this general condition of Krylov and Rockner, and prove well-posedness and propagation of chaos for the particle system. Okay. Is that clear? So, okay. So let's give the results, and then we'll speak a bit about the literature, and then I'll show you the proofs. So the first thing is you should understand that there is no structural assumption on B. So the only thing you know is this integrability. You don't know where B explodes, where B is not well defined, what's happening with B. And so in order to start understanding a little bit, you need to define some set of this kind, which basically for a fixed T tells you where your B is not well defined. So this is just a technicality. But like, if you look at the interaction that Nicolas showed you before, like something that is like this. So the set is just x equals y, right? It's just when two particles collide, you have something that's not well defined, okay? And so when you have this domination here, for each T, you know that you're in LP. This is of Lebesgue measure 0, but I kind of need to redefine the system and say that I will turn off every interaction every time I visit this ugly set. But that's nothing. It's like here also when you analyze this system, your kernel, this kernel here, you're going to say that this is 0. You're going to turn off an interaction just so the things make sense, okay? And so you redefine the system like this. You're gonna prove this is well posed, but then you'll see that this is not going to change the dynamics in any way, okay? So this is the system actually, and for this system, but of course I don't want particles to interact with themselves, but that's also nothing. It's like one less interaction among n and then goes to infinity, okay? And we will get rid of this, okay? So the first thing we prove is that there exists a weak solution to the particle system, given any initial, like, okay, let's say the particles are IID, but you can also, there is no assumption on the initial, they can all start from the same point, okay? And the solution is unique in law in the class of solutions that satisfy this, but this is basically because of Girsanov theorem. So anyone who, if you can apply Girsanov theorem, you basically have this uniqueness in law in the class of things that for which the interaction squared integrated is always finite with probability 1. Okay, so as I said, there will be a Girsanov transform here. And the Girsanov transform is gonna ensure that the addition of the NT sets is doing nothing. So because the particles are gonna be absolutely continuous with respect to like Brownian motions, independent Brownian motions. So the Lebesgue measure of these sets for each two particles is going to be almost surely equal to 0. So every time, basically, when you write this in integral form, like here integral in time, this is going, essentially, this is going to tell you that essentially the systems are the same. Okay? But as there is no structure in B, we need to add this. Okay? Okay, so that's the first thing you prove. And then once you have the existence, then you want to converge to something, okay? And so here I want to use the martingale approach. I want to converge towards a martingale problem at the limit. And the martingale problem is the classical, right, martingale setting, like there is the generator here for the limit equation. This must be a martingale. The Q martingale, there is the initial condition, whatever. But what's interesting and what you need to add in this formulation is that you work in a class of measures where the one-dimensional marginals are densities with respect to Lebesgue who satisfy this kind of estimates, okay? And these are basically, and this is an integrability property that is satisfied also by a Gaussian density in dimension D, okay? So basically what you impose, you work in a class of martingale measures which have continuous measures on continuous paths in RD, which have marginal laws who have this property. They have Gaussian behavior, okay? And why you do that, why you impose that, it's because that is going to help you make sure that what appears in the martingale in MT, that everything is well defined. I'm gonna comment on that, okay? So this is what I want to converge to. So I have my particles for n fixed, they are well defined, and I want to converge towards this martingale problem with the empirical measure. And thanks to the result of Krylov and Rockner, under this hypothesis on the initial condition, no, Rockner and Zhang, sorry, I know that there is a unique solution to my martingale problem. And I know actually more about the marginals. I know that they have Gaussian estimates punctually from their results, not just in LP. But I am very happy with just putting here an LP condition. I don't need to ask the densities to have punctual Gaussian domination, okay? Why? Because that's enough. The Gaussian estimates in LR are enough to make sure that all the terms are well defined. And this is a small computation that's going to be useful for later on, and we're going to see the LQ-LP norm. So if you want to make sure that this is well defined with the assumptions I told you and the fact that B is dominated by an LP-LQ function, so you get rid of this is bounded, you bound your B, and then you do like a small Cauchy-Schwarz with respect to this measure, okay? And then once you're here, holder, like you have your P, your Q, you want to make them appear, so you do one in space and one in time, one with P over 2, the other one with Q over 2, and what comes out is the LQ-LP norm. So that's the norm you want to make appear. This is the thing you know it's finite. And what's the rest comes from the Gaussian behavior of rho. And what comes out, so it's some negative exponent in time. And for this to be integrable, you get exactly the Krylov-Rockner setting, okay? So you arrange yourself very well so that your martingale, all the terms in your martingale problem are well defined thanks to some Gaussian estimates. And when you want to converge to this martingale problem, you need to prove that your limit at the end satisfies Gaussian estimates, okay? Okay, so then you can prove the convergence, but I need to assume a bit more on the structure of B. So I have to assume that B has some continuity properties outside of this set of singularities of the function B at time t. So I need to assume that, like here, basically, if you are not looking at 0, this is continuous, okay? So that's what I assume in addition, because I don't have structure. I assume that there is basically continuity outside of a zero measure set. And with that assumptions, you can prove that the empirical measure converges to the solution of the martingale problem, which is unique and can be related to your SDE. Okay. So, so in practice, is what I said here, the kernels, the interactions are usually convolutions that are well defined everywhere except in one point. So it's reasonable to assume that outside of that point, you have something continuous, okay? And as I am going to prove tightness, so I'm going to extract something that's weakly convergent, I need some continuity to use the weak convergence, so that's why I assumed that, okay? Okay. So an alternative hypothesis to this one would be that I don't ask for global LP integrability, but local LP integrability. And if I ask for local integrability, I'm a bit lazy, and I say, well, if it's locally integrable, then I just want it to be bounded at infinity. So I want the dominating function, basically, if it's bounded, then this is always true. But I want some kind of this condition, okay? Just so I could give finally an example, because that's what everyone asks when you work with these conditions. What's the LP-LQ interaction? What can it be? How much can it be singular, etc.? So typical example of B would be this one, which I took from Krylov and Rockner. So in dimension 2, you have basically something that's of order 1 over the distance to the power 1 minus epsilon. So you can't do this. but you can rather do something like this. Okay, that's like the singularity that is admissible. Okay, and so it can't work for the Keller-Segal equation. It can't work also for the Navier-Stokes. And it's normal, it doesn't work, because you don't use any structural property of the kernel here. You just use this local integrability. And so for Navier-Stokes, you don't exploit the sign here when the interaction is repulsive, so you kind of use that, right? So here you don't care if it's attractive or repulsive, so you're losing, okay? And also for Keller-Segal, it can't work as well. It's kind of a limiting case, because as Nicola explained you, these particles, they touch a lot, they collide, they do weird stuff. And if I'm going to use Girsanov, I'm going to be absolutely continuous with n Brownian motions, and then Brownian motions are not gonna behave like that. Okay. So in neither of the two cases, as I'm not using any structure, this can't work. Okay. So so about the literature. So before, when I started doing this, actually Jean-François told me that there is this nice work of all these authors here that consider large deviation principles for particles in singular interaction. And as a consequence, somewhere they prove an LDP for particles in LQ-LP interaction. And as a byproduct of the LDP, they have the propagation of chaos. Okay? But there was no direct proof like the usual one where you just take your empirical measure, you try to converge it. Okay? So we are going to try to give a direct proof here. We are going to give the direct proof here by using tightness and convergence argument. Okay? And not passing through LDP. So, and this is going to be very much related to the techniques we introduced with Denis and Jean-François. When we worked in but this goes very well with the previous talk, when we worked in this framework in dimension 1, so we are not Markovian, we are non-Markovian here. The interaction goes with the past, like Nicola explained. And in dimension 1, here you have the derivative of a Gaussian, and the techniques here are going to be closely related to this, the techniques we introduced here. Okay. So how does it go? And I tried, so the rest, I have 5, 10, well, I have 10, 15 minutes. I can, right, Sylvie? Yeah, more or less, a bit less. Always a bit less, it's better. I'm going to show you an example of an organizer that's giving a talk which is short and doesn't go over 45 minutes. So, so the existence is a Girsanov theorem. So we all know that you start from a Brownian motions on some probability space, and you want to add a drift. And what you want to add here, so this is the drift of the first particle, and this is the drift of the nth particle. You put this in a vector, and you want to consider the change of measure between these Brownian motions and your interacting particles. And obviously, if B was bounded, there's nothing to do, right? But these B's are not bounded. And we have to work a bit more. So, and to justify the change of measure, as usually, you do a Novikov condition. So it's enough to prove something like this. So for a fixed n, that this exponential moment is finite, okay, of this thing. And so this is very much in the spirit of Krylov and Rockner's paper. So what you basically do is this like a Kosminski estimate. So first, okay, you have n particles. You want to go to 2 by 2 interactions, but that's what also Nicola told you before. If you know how to how 2 particles interact, and if you know how to control that, first you need to control that to have existence. So this is what you do here. I do some Jensen inequalities, and I come to 2 by 2 interaction, exponential thing of here. And so this is nothing, but I lose a lot here with the Jensen because I introduced an n here. But doesn't matter, n is fixed, okay? I just want to prove it's well posed. I just want to prove the Girsanov works. So once you're here, you want just to control this object, and this is called the Kosminski estimate. So you prove that this is finite using the integrability properties that are given to you, okay? And this can be done for a fixed n by basically developing this exponential in a sum, okay, of these kind of terms, and then basically controlling for each k every moment of this 2x2 interaction squared integrated in time, okay? That's what you want actually to control for every k. And you're gonna get a sequence, and you want that sequence to be convergent, and that's gonna be your objective. But now you're with two independent Brownian motions. So what you need to do is you have to be very precise. You can't just put this k inside with a holder or whatever. You really need to be very, very precise. You need to iterate this integral. So you're gonna get rid of the factorial, which is not nice. It's gonna make your things local in time, and then you're gonna prolong it, but it's gonna work. And you're gonna iterate this integral, and then you're really gonna use the fact that there is a Brownian motion here, a Brownian motion here, and they are independent, okay? And I do it for k equals 1. I don't do it for k equals k, but that's very easy. So for k equals 1, these are two independent Brownian motions. I fix one of them. I condition with one of them. I use my LQLP assumption, so I dominate with H. And then as before, when I told you that the martingale terms are well defined, I use a holder in time and space, and I make appear the norm, okay, or LQLP norm. So all in all, I know how to control k equals 1, and then if you want to control k, as I told you, you iterate this, and then you start conditioning from right to left. You start to using basically all these things, and at some point it works, okay? The problem is gonna be, it's gonna be local in time, so then you also have to do like portions of time. For each portion of time you have to do something, but all in all, at the end it's global in time, and for a fixed n, your particles are well posed, okay? In this setting. So you can move from your particles to independent Brownian motions. And the cost to pay, you control it, okay? Great. So now you want to converge. But if you want to converge, your Girsanov transformation that we just proved is completely useless. It's completely useless because I was not that sharp. I introduced that n with Jensen inequalities. So I always had something depending on n, which basically was not sharp, and it's going to infinity with n, okay? So the cost I pay from moving to all the interacting system to Brownian motions is just not metrizable in n, okay? It's not uniform in n, and I need to work a bit more. So I give you here an example. So because I can't control this uniformly in n, if you want to prove tightness, you go to the law of one particle because they're exchangeable. And what you do is basically this thing, like Kolmogorov criterion, right? But then if you transform to Brownian motions, you pay something here, the thing coming from this estimate, and this is not metrizable. I don't know how to prove it's finite in n, okay? So it's not sharp enough. But then there is this nice idea that we exploited with Jean-François and Denis, and which perfectly came into place in this work, is that we use, I use partial transformations. So what I call by partial transformation is when I don't transform everyone to a Brownian motion, okay? I transform only a certain number of particles, which is always fixed, and it's always strictly less than n. So if I fix some integer between 1 and n, but it's not equal to n, I want to transform the first R0 particles to Brownian motions, and then the rest, I just want to remove the dependence of the first particles in here. So the rest interacts like the previous ones, but it doesn't see these guys, okay? And this is an intermediate transformation. It's a space that's intermediate between everyone is a Brownian motion, everyone is interacting. This is something in between, okay? So you basically have two packages. One that's Brownian motions that are independent, and the other one that are interacting things that they're independent from these guys, okay? So as you can prove that the big transformation, this is a subset of the big transformation, like the drift, the drift vector. So you know this is well posed by the previous thing. You know that this is going to be controllable. The Novikov is going to work for this as well, of course. But the thing is that with these things, you can get uniform estimates in n, okay, of these kind of transformations. And they are going to be extremely useful. So, and why is that? It's basically because there is less things to transform, okay? Less things to move, less things to control, and perfectly fits the framework again. And but it's less costly, and it's going to be uniform in n. So that's what I will try to explain from now on to the end. Why is it like that? So this is the drift vector for the transformation. So I need to remove all the drift for the first R0 particles. And then I need to remove all the interactions between all the other particles and the first R0 ones, okay? So for the other places, I just remove a portion of the drift. And that's the key, basically. So here I remove everything, but here I remove only a portion, okay? And then I just want to control, again, the Novikov thing, the Novikov condition. But now I can prove that the control is uniform in n, okay? And if it's uniform in n, then I'm very happy. As soon as I have something uniform in n, I'm going to use it everywhere, and then that's going to work. Okay, so why is this uniform in n, and where's the catch? And why they need to be organized like this? Why the packs need to be independent? That's what I'm going to just try to explain. So what we have here is the square of this vector. So I just write it down. So here you have all the interactions, and here you have the partial ones that you removed, okay? And here you do a small Jensen, okay? And now you see that if B is bounded, that's the first remark, if B was bounded, here you get something that's uniform in n. So if B was bounded, basically because R0 is strictly smaller than n, you do all this is of order R0 times B infinity square. Okay, so B is not bounded, so we have to work more, but that's kind of already tells you why it's going to work. So then you come back to a very nice Kosminski estimate, like before. So you separate the two packs by Cauchy-Schwarz, okay? And then once you separated them, you do again some Holder inequalities everywhere. So you go to 2x2 interactions. So now you came to 2x2 interactions, like before, but you have these coefficients here, which are extremely pleasant now. They are basically uniform in n, so they are going to be of this order. And what you have as well is that every time here, so if you look well at these indices here, so you always have a Brownian motion and something. And that something is independent of the Brownian motion. It's always the case. So the first R0 are Brownian, so this is your Brownian, and this is independent of the Brownian. And here this is the Brownian, right? Yes. And these are just independent from the Brownian. So you condition with one, they're dependent, and you use the Kosminski computations I showed you. But now all these things, there is no n in the exponential, basically. So you won, like you have a transformation, which is somewhere in between, but which is very pleasant to work with because it has uniform estimates on the moments. So then if you come back to my tightness here, you're not going to go to this space. You're going to go to the space where the first particle is a Brownian motion, so not to this. And then you're going to separate them, but now this will be uniform in n. And you have tightness. Okay? And so you use that one for tightness. And when you want to pass to the limit, you have to define some functional in which you evaluate in the empirical measure. So you basically plug your empirical measure in the martingale problem. You square that thing, and you look at all the terms. You use you see what you have, and then what happens is basically that you're always going to have something that depends either of 1, 2, 3, or 4 particles. So all in all, like you are, every time you want to control a term, you always use a partial transformation, and it's always uniform in n, and then everything kind of comes into place. So I'm not going to bother you with that. And also you have to prove the thing I added, so the fact that you work in a good class of laws, and there you use again the partial transformation. So easy, right? You use the weak convergence, and once you are there, like you use your partial transformation, and once you're on the partial transformation, you use your estimates with good exponents, etc. But it's important that that here is uniform in n. So this is going to be uniform in n. I forgot the limit here. But this is going to disappear. There's going to be a constant. And then you make appear everyone else in a good, with a good exponent. And you get, by Ries's theorem, that the limit is also how it's supposed to be, that it has a Gaussian behavior. Okay? So you're done. You're converging to the right martingale problem. And you have your propagation of chaos. So all in all, this is what they say a qualitative proof. So it's the proof of the propagation of chaos. There is no rate, okay? Sometimes they say weak propagation of chaos. And then probably you can work more to get some rates or whatever. And how I see this condition, I see it as kind of a limit for a Gersanov. So above that, you cannot hope to be absolutely continuous with respect to Wiener. You cannot hope to behave like independent Brownian motions. And that's also what you've seen in the previous talks, like your particles. If something is more singular, your particles maybe will not behave as independent Brownian motions, for sure. So that's one thing I comment on. And then, okay, here is the reminder of what kind of interactions it can work for. And then the question is, and this is for sure, the answer is yes, right? Is that if you look at now a non-Markovian setting in dimension D, so the one that has this delayed interaction, so you're not interacting with your particle at time t, but you interact with all the trajectories, how much can you improve the condition, okay? So in dimension 1, we did it with Jean-François and Denis, so we looked at the derivative. So the k was the derivative of a Gaussian in dimension 1. And this is not in LQ, LP with the good condition, okay? So if it would have been a Markovian interaction, like in T, like the one with the, if this would have been an interaction of this type, this would not work, okay? But as this integral is kind of smoothing a little bit everything, because you're not attracted by one point, but you're attracted by a whole trajectory, then for this, it works, okay? So then the question is, how much can you push that in higher dimensions? And why I am interested in that is because there are physical models coming from these chemotaxis models, which are like indirect chemotaxis models, where between the density of cells, between the density of cells and the chemical thing, you have an ODE, for example. And that's going to introduce, like even in the parabolic elliptic model, that introduces some path dependence. So it would be interesting to see whether this would work for another class of particle systems which correspond to some chemotaxis models. Okay? And that's where I stop.
So could you maybe clarify? To me, it seemed like the LP-LQ condition is coming from the fact that you want to apply Gersanov at some point, and if you are in the critical case, like if you have Gersanov available in the critical case for some further assumptions, but in the critical case, so with equality in the Krylov-Röckner condition, can you run the same arguments, or at which point would it fail if you would still have the exponential moment estimate.
So for me, I will not see it because my integral in time, you know, the one, when you make appear the LQLP norm, as a residual, you make appear some singular integral in time, like 1 over t to some power. And if you're in the critical case, that explodes. Yeah. So I will not be able to do that. But I think that the critical case for the linear process, for the linear particle, has been treated. So I have to go and see what they did. But they did something in the critical case. I don't know if there are some other assumptions. But as it is like this, the condition on the exponents really appears because you want something to be integrable. So as long as you're in the critical case, it explodes, and I don't have a sharper estimate at the moment. Okay,
thanks.
You're welcome.
Other comments? Okay, no. So thanks again.
Thanks, Evie.